Okay, everybody, good morning. You made it. So as I was saying before, we have quality this morning rather than quantity of students. So well done. Grab the coffee or the donuts or whatever you do to wake up. Now, a couple of things. Don't forget, next week, an important week for this course, lab test 1. Okay, so what do you need to bring to the test? You need to bring your student card, right? The paper will be provided. You know, like, because I've been here a long time, I've seen lots of stuff happen in examinations. One old chestnut is students impersonating other students. So they'll like have the card and they'll be wearing a wig and they'll show me the student card and they're like, that's me. I'm like, no, it's not. Okay, so just don't cheat, right? Like, I know you won't, but there's an old saying, if you're not smart enough to pass the test, then you're not smart enough to cheat and get away with it, okay? It's pretty accurate. All right, so anyway, it's 15% of your final grade, and most people do really well on class test 1. Okay, you should be aiming for full marks. Okay, go for 100. Okay, I know you can do it. All right, so this week we've been looking at integration in higher dimensions. Okay, and we could relate it with what we learn at school through area and a little bit of volume too, okay? So in the top picture, that's like your standard Riemann sum. You're using rectangles to approximate area, and then you sum them up and take a limit. In the higher dimensional case, you're using little rectangles, say in the XY plane, right? And you sort of shrink the size of those rectangles and add them all up. Okay, so we've learned a few things. One was how to reverse the order of integration. That is an important skill in this course. Okay, good morning, well done, you made it. You got the coffee, good. Good, yeah. Okay, so this example from yesterday, I think it was, is a super important method for this course. Can you come down? Just come down and join us. Like, why would you sit in the back when there's like 20 people here? You're sick? Go home. Like, you can just, if you're too sick, it's better to be at home, you know? But if you want, you can, this side's free, but just, you know, when I look up and it's 9 a.m. and you're in the very last row and there's like 20 people here, it's just, you know, it's not great, but get well soon, okay? Get well soon. All right, so this is a very important skill for this course. And the motivation behind it is you can't do that inside integral in the regular, you know, inside-outside way. So we flip the order. So instead of dx dy, we redescribe the region and we get dx, instead of dy dx, we flip it and we get dx dy, all right? Now, I did show you or at least I mentioned when I did this example, there is another way that you can solve these problems using integration by parts. So I'll do that. I'll do that maybe in the second lecture. But they don't really want you to do it that way, okay? All right. We also looked at area, right? We also looked at that, so that was good. And this was, I think, where we ended. Polar coordinates. Let me just zoom out a bit. Okay. So in polar coordinates, we're not using x's and y's, so horizontal and vertical dimensions. We're using coordinates in terms of length r and angle theta. Okay. And instead of having dx dy or dy dx as your area element, over here, this is the area element in terms of polar coordinates, okay? So it can simplify a lot of stuff, which is great, and we'll be looking at a little bit more of that today. And there was a little shortcut that I mentioned, the B theorem, which basically simplifies calculations for you with double integrals as long as you've got constants in your limits of integration. So you're integrating over a rectangle, you've got the product of two functions, you can basically split it up and multiply the two integrals, the two single integrals together. That is can be a time saver, okay? It can be a time saver, which is great, which is great. Okay, so let's talk about today some sort of connections with mass and centres of mass and centroids, centres of area, that sort of thing, okay? But before we get there, and I'll fix up that focus. Before we get there, let's just do another example. Now, you can see with this one, it even tells you evaluate it by using polars, but sometimes you're not told. You just give it an integral and you've got to evaluate it somehow, right? So what is a good check for using polar coordinates? Okay, what is a good sort of trigger? Anybody know? Yeah. Yeah, drawing it, and do you get sort of curved surfaces or curved regions? That's a very good one, right? And seeing square roots is also a pretty good trigger, right? So you're absolutely right, okay? So we're going to draw it, yes. And I'm actually going to do this using polars. I think in the associated video, I do it without polars. So it's not necessary, but maybe it's a little bit helpful, okay? So let's remind ourselves. So in polars, that's the most important information. Now, you won't get that in your tests. I don't think you'll get a formula sheet for that, so you need to know that. But let's draw a picture. Let's start with your advice and draw a little picture. Okay, so in this case, y is between 0 and 2, x is between negative of that square root and the positive of that square root. So let's actually just write it out. Okay? So it's not super clear what region this actually is. Okay, the square roots cause a bit of confusion, but one way to simplify it is basically square that, set x equal to, say, that, and square both sides. Okay, that's sort of the problematic one, that's the easy one, right? So let's actually square that side and see what happens. Oh, sorry, y squared. Okay, so going off that, let's move things around a bit. Okay, and that looks a little better. But what do we think this might be? Does anybody know? What sort of geometrically, what are we sort of going to discover here? Anybody have an idea? What sort of curve is it going to be? Yeah, it's probably going to be a circle, right? But let's actually work it out and see how we can do that. One super helpful thing in this regard is an idea called completing the square. So basically you've got that and you want it to be the square of something. You've already got a square there. So what you do is you look at the coefficient of y. Yeah? It's -2. You take half of it and you square it. And you add it in. Okay? So the coefficient of y, you halve it, you square it, and you add it to both sides. Okay? So what's the significance of that? It actually looks like I've made it more crazy. Well, this is now a perfect square. Y minus 1 all squared. Okay? So we've got x squared plus y minus 1 all squared equals this thing, 1. So yeah, it is a circle. Okay, it is a circle and it's got radius 1 and it's centered at x equals 0, y equals 1. Okay, that little bit of information helps us draw our boundary. Okay, so let's actually draw it in. Okay, so that's going to be the center of my circle. Okay, that's my crazy circle there. There's 2. Okay, so for y between 0 and 2, that's the line y equals 2. I'm basically going to be in that strip, and then I intersect it with the circle. So that's going to be my region of integration. Okay? So it took us a little bit of work, but we got there. Okay? Great. So how are we going to set this up in polars? Yeah, come on down. Okay, so basically, how are we going to set this up in polars? This is sort of the question, right? So I've got this sort of boundary for the circle, yeah? What I can do is I can replace x with r cosine theta and y with r sine theta and expand it. Okay, that's one way of doing it. You don't have to do it. You could say, oh, okay, I'm going to just take that branch and y's between those two things, and I can just set up my integral that way. And I've done that online, but I'm not going to do that, right? So I'll do it using polars in this case. So from this representation, yep. Okay. So if I expand that and use cos squared plus sine squared equals 1, I'll get the following. And I'm just going to move things around and factor them. Okay. Now, r can't be 0 here because I'm not going to get anything if r is 0. So I'm going to ignore that bit. And this is the bit that I want. So we're going to ignore r equals 0 because it's useless, right? It doesn't actually give us the thing. That's what we wanted. So that curve is r equals 2 sine theta. Okay, so you can see now that setting up the integral is often the most involved case. Doing the integral isn't that hard usually. Sometimes it is, but not always. Okay? So, I know it's early, maybe you haven't had your coffee yet, but who can describe the region omega in polars. Who can describe it? Come on, take the morning challenge. Who can describe it? I can get to you. This is one of the benefits of like having lots of space.
I would say that theta is 0 to pi, and r is going to be 2 sine theta.
But we want inequalities for r. So r is bigger than something and less than something.
Oh, r is bigger than 0 and smaller than 2 sine theta, sorry.
Yeah, that's it. Yeah, exactly. 100. Well done. Okay, so let's deconstruct that a bit. Let's get the angle first. If I start here at theta equals 0 and I rotate anti-clockwise, to sweep out the whole of that circle, I need to do half a revolution. So you're absolutely right. Yeah? Now, if you're not sure about the other bounds, start in the center and just draw some lines that go out. Okay, it comes into the region, these lines start at r equals 0 and they cross at r equals 2 sine theta. Boom. Where did the cos go? Cos squared plus sine squared equals 1. That's what. So to go from, so there's a question on, to go from here to here, to simplify it, you're using cos squared plus sine squared equals 1. Okay, that's it. So what does our integral look like? Well, so now we're working in polars. We're going to replace x with r cos theta and y with r sine theta. So r squared cos squared plus r squared sine squared square root. Right? That's going to simplify massively. Okay? And you've got the area element there, r d theta. Okay, so this is going to simplify. This is going to simplify. Okay, you're going to get r from there. You're going to get r from there. Boom. Okay? So that looks a lot friendlier, at least on the surface, than what we started with. Okay? But you could just use Cartesians, no worries. If you want to do that, if you don't like polars, you can do it. Right? So now we just need to integrate this. So this is going to become 1/3 r cubed. So if you do the first integral, according to my calcs, you'll get something like this. And now, it's just a matter of integrating that. Okay, so remember Math 1231. This is where you'd see a problem like this. And you go, when am I ever going to use that? Now is the time.
For the bounds of theta, is it measured from the origin while the bounds of r is from the center of the circle?
Oh, yeah, sorry, hang on. I'm drawing those lines wrong. You're right. So hang on. So it's still correct. Sorry. When I'm saying from here, drawing it. Sorry, you should be starting at the origin. So that blue, that's better. Okay. Yeah. So those black lines. Sorry, I thought that was the origin for a second. So that's it, right? And then where does theta 0 along that line? Theta's pi on 2 there. pi there, 3 pi on 2 there. Okay? Yeah. Good catch. Yeah, so start your R at the origin. Start your R at the origin, not at the center of the circle. That's a mistake. Okay? So, can anyone remember? Think way back to Math 1, 2, 3, 1. What can we do with this integral? Seems a bit painful at the end, right?
You split the sine cubed into like sine theta times sine squared, and then sine squared can be changed to 1 minus cos squared.
Good job. Okay, so that's one way to do it. There are other ways to do it. Now, let's just check to see if this is on your formula sheet. Let me just check to see if this is on your formula sheet. Okay, Laplace transforms, we're going to see those. Fourier series, we're going to see those. Leibniz rule, variation of parameters, and basic integrals. Ooh. Sort of. Okay? Sort of down the bottom. I'd have to investigate that further. Okay? But that is definitely something you should study carefully before the final exam, right? Because sometimes in the exam you're stressed and, you know, I forget stuff all the time and you're not sure what to do, right? At least the formula sheet gives you something to look at. Okay, so back to the program. If I was doing this, I'd take the 8 on 3 out the front and then do exactly what you said. I would write it like this. Yep. And so when you expand that, you're going to have an integral of sine times cos squared, which is like they're easier to do. Okay, so when we integrate this sine, it's going to become a negative cos. When we integrate this, it's going to be something like cos cubed. Okay, we just got to touch up what it's going to be. So when I differentiate this, the 3 is going to come to the front, negative sine is going to come to the front, but I only have 1 here, negative 1, so I want to divide by 3. If you don't like that, you can use the integration by substitution. But I would avoid that if possible. Like, it's the same as, you know, integration by parts. I'll show you integration by parts later, but just avoid it. The same with, anybody do discrete here in first year? Anyone do discrete maths? Yeah, so you remember proof by induction? Gosh, what a lot of effort, right? Like sometimes you can't avoid it, but I try as much as I can to avoid it, and there must be another way, okay? Questions, comments, observations, criticisms. What is on your mind? Now, if you don't want to use, if you don't want to use polars, you could do it just using x's and y's, Cartesians, all that good stuff. I've done a video on that. That's where the link takes you. I've done it that way. I think this is just as good. They're both not straightforward, right? You can't just write down the answer. Sometimes you can just write down the answer. But let me know what's on your mind. What's happening at home? How many people have we got at home? The true believers. 26. Okay, let's put this up. This is a good question. How did you go from the inequality to a general equation? Oh, I just set them equal. So we're interested. That's a really good question. So let me put that one up there, and that one up there. So everyone here, right? So we're interested in the boundaries, the edges. Okay? And so, you know, x between that and that, to get that edge, I'll set that x equal to this, because that's what happens at the boundary, at the edge. So I think that's a pretty good strategy if you're not sure what it looks like. Just set one of the variables to, you know, x equals square root 2y minus y squared. And then see what happens. Okay? All right. Oh, there's a response. That a bit better for people up the back? I think he did that to get a picture of the plot. Yes, Kyle, you are correct. And Julian, thank you for your question. See, people think it's anonymous when you post here. It's not anonymous, right? I can see who you are. But that's okay. Where did the cos go? I'll just there. All right, other questions? Yes. Special delivery.
How do you go from cos cubed to the final integral at the very bottom?
Cos cubed, sine cubed? Yeah. So. Oh, at the very bottom. Oh, okay. So let me move that up a bit. So, you know, you put in theta equals pi, you put in theta equals 0, you take, you know. Yeah. Yeah, so if you're not sure about that, right, so the nice form of that is that's the derivative of, well, sort of, even if you include the minus sign, of cosine. So it's kind of using the chain rule backwards, which is integration by substitution. Yeah, so if you're not sure, you can always do those methods, right? Yeah, but it takes a bit more time. Yeah, Math 1231, remember? Did you take that course? Yeah, so it's easy to forget if you don't use it. It's like language, you know. If you're not speaking a language, a second or third language every day, or, you know, regularly, it's like, I've forgotten that completely, right? Other questions? Okay. Yeah, but can you see, I know whenever I teach first year, I always say, oh, you'll use this next year to the students. I say, oh, if you're doing 2019, you'll use this next year, right? Can you see how this is really connected with first year, right? Like all the ideas. Okay, let's move on to some of the other bits. So this is sort of an application in a general sense, in a sort of loose sense, I guess, of double integrals. So what can double integrals do? They can compute area, they can compute volume, but they can also do things like compute, you might have an object, like a thin plate or something, and the density of that plate changes depending on where you are, right? You can use double integrals to compute the total mass of the plate. You can use double integrals to compute the moments, right? The moments about the axes. You can use double integrals to compute second moments of inertia. You can use them to do all sorts of stuff. So we're only going to scratch the surface here, but it is important, okay? And it sort of gives you a way to connect what you're learning with something a bit more physical, if that makes sense. So let's go back to this old chestnut, right? Centroid, it sounds like, robot, centroid. What is a centroid? Anybody know? Centroid, what is it?
Centroid means the geometric center of an object shape.
Yeah. And so you're absolutely right. What about center of mass? When you talk about center of mass, what is a center of mass?
It's the point at which you could, I guess, balance an object if it was, not even.
Yeah. So let's try it. So, I don't know. If I was trying to find, this will do. This won't hurt anyone, right? Try to, pressure. I can't do it. But you get the idea, right? If I put my finger under here and the thing balances, right? You're sort of getting close to the center of mass. It's like you said, a balance point, right? Yeah. So with a two-dimensional thing, I don't know, let's just take a piece of paper, right? Centroid is a bit like the center of mass, sort of a balance point as well. But really, what's the center of this shape? You would sort of go, okay, well, sort of in the middle, right? So it's sort of like a balance point. So how can we use double integrals to calculate this point? Now, before I go on though, why would you want to know something like that? Come on, you guys are engineering students, right? Why would you want to know the center of mass of an object? Like, anyone doing mechanical here? Aerospace or aero? Yeah, okay, a few people. So when we talk about the center of mass, it's, let's say this microphone, right? This microphone's got a center of mass and it's moving around, okay? If we can find the center of mass, it's a bit like that, at that point, we can control the object by paying attention to that center of mass. Center of gravity is another one. So, you might see racing cars and they have a very low center of gravity, right? They can calculate that, they can control the car better. So from a mechanical and design point of view, the points are important because knowledge of that points helps you control movement, okay? So that's it's super interesting, okay? All right, so let's read the question. Calculate the centroid of the region that lies in the first quadrant of the XY plane and is bounded by that circle, okay? So draw a picture, as we do, right? Yep. Okay. Now, let's not do any calculus. Let's just actually look at the picture. Okay, I know it's still early. Is there any symmetry in that picture? So there's kind of a fold symmetry, if you want to call it that way. But the line would be y equals x, right? You can fold it and, it just covers each part perfectly. Okay? So for these kind of problems with centroids, center of mass, center of area, whatever, it's very symmetrical. And the points, if there's symmetry, the points lie on lines of symmetry. Okay? So this can be a huge time saver. You don't actually have to go through and calculate all the double derivatives, double integrals or whatever it is, if you can see the symmetry. Now, some people can see it, some people can't. It's a skill that you can improve, right? Sometimes I see it, sometimes I don't. Okay? But it can be a huge time saver in the exam. Okay? So, what do we use for these centroid calculations? Well, if we can't see symmetry, these double integrals are the way to go, okay? So, what do they mean? Well, these top bits are basically their first moments about the axes, right? And the bottom is just the area of the shape. So it's a bit like an average, because you're dividing something by something else, but that's the way I remember it. It's the first moments about each of the axes divided by the area of the shape that you're working with. Okay? So that and that, they're known as the first moments, at least in this case, and then the bottom bits are the total area. Okay? So let's use that. And with the total area, if your shape's nice, you don't even have to do a double integral. Right? That's a disk with radius A. You wouldn't do a double integral to calculate the area, right? Oh, pi A squared all on 4. Finished. Okay? So we want to work smarter, not harder. Okay? So we're going to use these, that, and that. But we only need one of them, people. Why? Because symmetry, right? Because I dare you to write that in your... final exam. Because symmetry. Okay, I would give it full marks. Okay? All right, so let's get one of these and then we have the other one. Okay. So what should we call this? Let's call it omega. Yeah? Easy, no double integrals required, which is brilliant. Okay? The next thing we're going to do, let's calculate the x-coordinate of the center of area. So it's this first moment divided by the area. So basically we want that double integral. Okay. That's what we want to calculate. Okay. Now, polar coordinates, anybody? Right. It's a curved region. I think it makes sense to consider polar coordinates here. Right. What would it be? What would the description of omega be in terms of, oh my God, sorry, in terms of r and theta? Come on, what are the limits of integration going to be? Come on, people. Someone, anyone.
0 to pi on 2.
Yeah, and what about the r? Go for gold.
0 to a.
Yes. Perfecto. Okay, so this is not a difficult region to describe in terms of polars. So we do a quarter, we start there, we do a quarter of a turn, anti-clockwise. And we start there and we just draw a line out. It enters at r equals 0, it leaves at r equals a. Okay? Bump, bump, bump. So let's do it. So I'm going to replace x with r cos theta, right? Okay, so x becomes r cos theta, and then I'm multiplying by this r. So that's that bit, that's that bit. Right, that's the area element from up there. So we're going to get r squared times cos theta. Now the B theorem from yesterday. You can split this integral up into the product of two single integrals, if you want to. If you want to. Because it's r squared times cosine theta, right? So I would just split it up. B theorem. And then you can work that out, which is pretty easy, right? Or it's easier. Okay, if you work it according to what I got, it's a cubed on tree. All right, so we've got that, and we want to divide it into that. And then we know y bar is going to be the same as x bar. Okay? So in this situation, the centroid or centre of area, it lies within the shape itself. And for most simple shapes, that's true, but it's not always true. Okay? Especially when we get onto problems involving where there's a density function, and depending on where you are, the density changes and stuff like that. Okay? Questions? This is 4A, by the way. 4A. Yes. Hang on. Everyone at home. You made it. Well done. Welcome. Yes.
Why do you divide the two integrals at the end?
Oh, yeah. So think of it as like an average, right? So, you know, if we're using, the way I look at this formula, right, is that the x component, you've got the first moment to about the y-axis divided by the area of the shape, okay? And it's the same with the second one, right? This is the first, what we call at least in this situation, the first moment to about the x-axis, and you're dividing by the... so let me say a little bit more about that. You're dividing by the area. Let me say a little bit more about that. Okay. So, yeah. So let's say you have something like this. So we would call these first moments. Oops. Okay, sometimes there's a density function in here. So the rho okay, and so basically I sort of think of this as distance times mass. Okay, and in the really simple examples that you might see at school or in first year, that's what they do. But in this case, for just a shape with no density function stated, you can just think, oh, okay, well, the density function in this simple case is just 1, okay? It doesn't change. Okay? All right, should we just set up another one? How are we going for time? Oh, yeah, we've got 4 minutes. Okay. Let's set up another one. No, you know what? Let's not. Questions? I'm not going to rush through something in like 3 minutes. Let me move that down a bit too. Okay. So, will you get this in the final exam? Maybe. Will you get the formulae? I didn't see it on that sheet. Did you see it anywhere? Let's have a look. So I see integrals, I see differential equations, I see Taylor and Leibniz and Fourier and that, but I don't see any of these double integrals. Okay? All right, let's take a break. Start again in 10 minutes. If you've got questions at home, let me know. Go grab a coffee or a drink or something, and I'll see you back here in 10 minutes. If you have any questions, come on down. Here I've just written down what's called the first moments of a shape or a solid or a region. Basically, here the rho function is like a density function, so as you move around the shape, maybe the density changes, okay? And these things are sort of the more general way if you have a non-constant density function. In these things, you know, the first moments up the top, I mean, you're not told anything about the density in the you know, for a two-dimensional shape, right? So you can think of it just as constant. So the way I remember these ones is these are the first moments about an axis, right? And so this is like the first moment of about the y-axis. It's distance, basically distance times mass, right? And for this one, it's the first known as the first moment about the x-axis. And again, it's like roughly speaking, it's distance times mass. So that's why there's an x and a y in there. That's measuring distance to an axis. And the rho and the dA roughly in a very loose manner is kind of measuring mass, okay? Because, you know, mass is density times area or density times volume. Okay, so that's the way I look at it. All right, so let's do the one down the bottom and see if we can set it up. I won't compute it, but I'll just set it up, because setting it up is actually the most challenging part in many of these problems. Okay, calculate the centroid of this shape. All right, so you're probably seeing the pattern by now. Draw in the boundary of the shape. Okay, so y squared equals 2x is going to look something like this. Yeah, Yeah. Y equals 4 minus x. That's going to look something like this. And y equals 0 is just the x-axis. So, okay. So if we look at the region bounded by that in the first quadrant, that's what we want. Okay, and we want to find the center of that shaded region. Okay, now the first check is symmetry. Can we see any symmetry there? I can't see any. Can anybody see any? I can't see any, right? I can't see any folding symmetry or lines of symmetry. I wish I could, but I don't think it's there. Okay, so we need two things. We'll need the area of the omega, and we'll need the first moments in a very sort of loose setting in 2D. Okay, so how are we going to describe this? Well, you can, this is the line, you know, y equals 4 minus x. This is the curve y squared equals 2x. So if we're going to describe it, how would we set it up? Well, you could find that intersection point and plot it down there, and then, you know, go with the y between this curve and that curve and the origin and the x-axis. I'm not going to do that. I'm going to go this way. Does anybody know why that's simpler? So when I'm describing my region, I'm going to use, not x. X. X is between there, and y is between these two vertical lines. Okay, so that's 4. Okay, sorry, I wrote that down. I don't know my horizontal from my vertical. Now, why is that simpler? That's the question. Why is that simpler? Anybody know? Why can't I do it using a sort of a vertical line and go that way?
Is it because when you do like vertical lines, you have like two regions that you need to do separately, whereas if you did it horizontally, it's pretty much just an area between two curves, and it's just like one entire thing.
Yeah. So that's exactly right. So it's to do it this way is a time saver, because the geometry of the region is simpler when you think about this. So let's just write it down, and all right, so x is to the right of this curve and to the left of this curve. Okay, so let's write this in terms of x. Okay, it's the same curve. So x is bigger than this curve, but less than this curve. So the way I would do that, I would say, okay, what's that going to be? That's going to be x equals 4 minus y. Okay, and now I need two parallel vertical lines, so y is going to be between 0 and 0 and 4. Okay, just imagine, 0 and 2, sorry. Okay, so that's going to be your 2 there. Okay, so in this case, I'm not drawing it very well, this is going to be your infinite strip. This is going to be your other part, and where they intersect is the shape that you want. Okay? Yeah. Now you can do it the other way, but it'll be more work. Okay, you have to do 2 integrals rather than just a single double integral. Okay? Questions? Questions? So you're either using two parallel horizontal lines or two parallel vertical lines and then a combination of other curves. Okay? You choose, but one is usually easier than the other one. Okay? All right. So let's leave that there. I'll leave you to finish that one. You've got the answers here. I think they're right. But let's look at something with a bit more punch. Okay? So one of the classic applications of double, triple integrals is determining things like total mass. Okay? So what's the most simple formula for mass? Right? So the total mass is density times volume. Right? So you got something okay, you want to compute that in, say, a two-dimensional or three-dimensional region. We're going to use double integrals, at least for that. Okay. Now, sometimes in this, in a sort of an ideal world, when we're in the 2D setting, we might remove the word volume and put in area, very loosely speaking. Okay. All right. So let's look at our question. A thin plate occupies a region bounded by these curves. If we associate the density function rho by this, where A is just some positive constant, then calculate the total mass of the plate. So as you move around the region that the plate occupies, the density changes, right? Maybe the material's changing, maybe there's something else, maybe the different thicknesses, right, as you move around. It's an idealized model, but you can kind of make it fit your imagination. Okay? So let's draw a picture first. All right, so y equals that. So that's the top part of a circle. And then x equals positive and negative a, so that's there and there. And then y equals negative a, so that's there. That's your shape. Okay? That's your shape. So you want the top half of a circle, and then the bottom half is going to be like a rectangle or something. And so as you move around, the density is going to change, right? So if you it's sort of less dense here, or actually less dense here than it is up here. Okay, so let's work that out. Okay, the double integral way of expressing this is to look at the double integral of the density function. Okay, so if you can't remember it, and sometimes I can't remember it, I go back to the simple formula that maybe you learn in physics. You know, mass equals density times volume, right? And like from a slicing point of view, Riemann sums, all that jazz, you slice it up, you calculate the mass of each little rectangle or each little part of the plate, and then you add up all the masses. That's where the double integral comes from. Okay? So, you know, you can kind of think, well, this thing at each point times the area, and when you sum that up, you get that. Okay? Sum it up, take a limit. That's what you get. Okay? So we know how to compute double integrals. We know how to set them up and evaluate them. This just gives it a little bit more of a, I guess, an engineering or a physical feel to it. Okay. So back to the program. We want to compute the mass of this thing, the total mass. Okay? How can we do it? Well, I'm going to look for simple shapes inside this shape. Okay, you could say, well, maybe I can use Cartesians, maybe I can use polars, but I think you can use both, right? So if you look at the top part, that looks like this bit looks like you could use polars. Am I right? Because it's curvy, right? Whereas the bottom part looks like you could just use Cartesians. So there's nothing stopping you computing the two masses, total masses, separately and adding them together. In fact, that's what I'm going to do. Okay? On YouTube, I think I do it a different way, but that was a long time ago. All right? So think about maybe this being omega 1, this being omega 2. Calculate the mass of omega 1 and the mass of omega 2 and add them together. That's one way of doing it. Okay? So, before we do that, let us describe the regions. Okay? So the total mass is given by this, where rho is the density function here. Okay? But let's be a bit cunning. And compute the two bits separately. You don't have to do that, but let's just try it. Okay? Let's just try it. So, okay, omega 1, people, let's use r and theta. How would we describe the omega 1 region in terms of polars? So the top part, how would we describe that in terms of polars? Come on, it's not difficult. We're more than halfway through the lesson. Come on. Yes.
Is it pi squared divided by 2? Pi a squared divided by 2?
Oh, not the area, just the region. So how do you describe omega 1 in terms of r and theta?
So it's, theta is between 0 and pi, yes. And r is between 0 and a.
Correct. On how? Good work. So that's a pretty easy region. Sorry. Okay. What about the second region? Let's do that with regular Cartesians. Okay? So x is going to be between negative a and positive a, and y is going to be less than 0 but greater than negative a. Okay? Let me just check at home what's going on. Okay. Can you just do Cartesian? Okay, let's put this up on the screen. It's a good question. Can you just do it with Cartesian? Yes, you can. In fact, that's the way I did it on YouTube like 15 years ago. But I'm just showing you something different. Okay? No, there's nothing stopping you from doing it. In fact, anyone who knows me would understand that like if you can use different methods to prove something or solve something, you should use it, right? You should use it if you want to. Okay? All right. Okay, so let's look at the mass now. There's our function, okay? So, you know, sort of as you go up the x-axis, the density of the plate or whatever it is increases. That's the way I would interpret it. Okay, so the mass of omega 1 plus the mass of omega 2. So let's do, what am I going to do first? Yeah, let's do the mass of omega 2 first. That seems pretty easy. Okay, the order doesn't matter here. Okay, so that's our first integral. You can see that what we're integrating doesn't actually depend on x, so it's a pretty easy integral to do. Okay, you would just multiply by x and put in that. Okay, now it gets a little bit more difficult. I'm integrating with respect to y, so y plus a, you could write it as a squared. Okay, you put that in, you'll get some cancellation in the second term, but the first term gives you a cubed. So with that density function, the total mass of that bottom part of the plate is a cubed in the appropriate units. Okay? Let's do the mass of the top, and then we'll add the two masses together. All right, so now we're going to work in polars. Okay, so so this is what we want to look at. And we want to put that into polar coordinates. Okay, so it's a little bit more difficult, but let's try it. Okay, so 0 to pi, 0 to a. Rho is y plus a, which is going to be r sine theta plus a. Okay, so we're feeling good because we could set it up. Now we just got to evaluate it, which is great. 2a, where did the 2a come from? When you put in a and negative a, you'll get two lots of that, okay? Because this doesn't depend on x, you basically multiply this by the length between the limits of integration. That's basically what you're doing. Okay? All right. So let's integrate. So we're going to have an r squared and an ra, and let's do the inside integral first. Okay? So that's going to become r cubed on 3. And AR is going to become AR squared on 2. Okay? And so you put those in, and you're going to get this. So now it's a single integral, you know you can handle those, and so you just integrate. There's no nasty sine cubes or cos squareds or anything like that. So this is actually pretty accessible as long as you can set it up. Okay, so you integrate that, sine will go to negative cosine, that'll become a theta next to it, and you should get this. You should get this. Sorry. Actually, I'll write it out in full. Okay, so simplify that, you've got your a cubed up there. I'll just shove it down here. So add that to that, you'll get this. Phew. Okay. So that's one way to do it. You can see it's a little involved. You've got to keep track of a number of things, the two different masses that you're calculating, and then you just add them together. Okay? Now remember, with Mobius, you can see I haven't finished that last bit, but do you really need to in Mobius, right? Simple things like arithmetic or simplifications of like terms, you don't actually need to do that, right? Questions? Okay. All right, questions online. Okay, here we go. So let's have a look. Can you just do it with Cartesians? No, you can do it like that, like I said before. Sorry, just one Cartesian area, not two Cartesian areas. Yes. Okay, so that's a great question. So, hang on. Who's asking this? Julian, you rule. You're wide awake. Yeah. So let's go back to our picture. So the question is, can you describe this region in terms of one set of x, y coordinates? Can you do it? Julian, what do you think at home? Oh no, it's not worth money. Like this excellent remote control could be yours that I've just found on the lectern, right? This water jug. What do you think, people? What do you think? Can we describe it using just Cartesians, not splitting it up, not using polars? Yeah, not using polars. I think that's the question that Julian's asking. Just one total Cartesian areas, no polars, no nothing. Just x and y, just x and y. What do we think, people? It's all about the access, right? Yeah, sit down.
Can you just like move it up by a? Just plus a on everything?
Oh, not a bad idea. So the suggestion is to move the, translate the region. Is that what you asked? Yeah, maybe. I think it's even simpler than that. Yes.
Can't we just say that it's less than the top function?
Mm-hmm. So what's the top curvy part, right? What's the top curvy part? It's given to you in the question. Let me move it down a bit. That curve yeah? And so if I'm using my y, I want y to be bigger than that and less than that. Okay? So is it possible to describe this? Yes. Right? Yes, it is. So what would it look like? I'm glad you asked. It would look like y is greater than negative a and less than that square root, and x is between negative a and positive a. Okay? So you've got, there are your parallel lines. X is in that strip, and y is between that curve and that curve. And in fact, if you look at the YouTube video, that's actually the way I did it on YouTube. Is it better? I don't know. But it's good to have options, right? In mathematics, and probably in lots of other places, if you can't solve a problem by using one method, then you choose a different method, right? This is very common. But you need to know that there's different methods. Other questions? Other questions? All right, let me show you something, something that's quite close to my heart and mind. All right. Sorry. Like I just dropped the mic. Okay. Now I told you there was something about this that could use integration by parts. Okay? So I wanted to say a few words about that. Now, I don't think anybody, I did some research on this and I published some stuff about it. I don't think anybody really cares, but since you're doing this course, you'll maybe care about it. Some people come to me and they say, I just can't visualize stuff. And that's fine, I get that, right? Like there's all sorts of people that, that I work with and they have strengths and, limitations. I have them too, right? So what happens if you're not very good visually with this sort of stuff? Okay, well you work on it. You improve your visual and spatial thinking skills, great. But it's always good to have options. It's always good to have options. So one option that I came up with was integration by parts. Integration by parts. Okay? So the nice thing about integration by parts is that you don't have to draw a picture. Okay? You don't have to draw a picture. If you don't want to, you don't have to. So let me show you how I do it. You don't have to describe the region either. Okay? So let me show you. Let me see if I can put it in here. Do I have it? Oh yeah. Yeah. Okay. So I'm going to show you something magical. Instead of doing the inside integral first, which you can't do in this problem, what happens if I did this? Okay? I'm inserting a 1 in front of the second integral. Have I changed the integral? No. Right? Still the same thing. Okay? But what do I notice now? The thing inside that integral is a product. Right? Now, in first year, we do this stuff all the time. You insert a factor of 1 into something, and it does something, it helps, you know? So, how do we integrate a product? Integration by parts, right? Integration by parts. So can you do it with this? Let's see. Let's see. This could be like u dash. This mess can be v. So, and it's all functions of x's, right? X, right? That's y's, but that'll disappear when you've integrated it. So, u is going to be x. V dash is the derivative of that. Okay? Hello, Math 1131's calling. It's a fundamental theorem of calculus. Yeah? So, if I can differentiate an integral, you could use Leibniz rule here, but that's overkill, right? Okay? What happens? That will become a negative, the 3 comes to the front, and then you replace y with 3x. Okay? That's probably the hardest part. It's the fundamental theorem of calculus. Or Leibniz rule, however you want to look at it. You're down with FTC? Yep, you know me. So, what's the integration by parts formula? Okay, the integral of u times v is u times v minus the integral of this product. Okay, so let's write that down and see what we find. So u times v. Minus the integral of the product that we just found. Okay, so you've got a minus and a minus, it'll become a plus. Okay, so let's slow down and see what we've got. What happens when you put x equals 4 into this? What value do we get? 0. Why?
12 to 3x. If you sub x equals 4 into 3x, it's just a line which you can't integrate.
Perfecto. So I've got a 3x in my integral sign. If I put in x equals 4 there, who cares about that? I'm integrating from 12 to 12. So that's got to be 0, right? It's like integrating over a point. That's got no area. What happens if I put in x equals 0 in here? Well, that'll be 0. And you're multiplying by 0. 0. Now, the only thing we've got left to do is this integral. Now, how good is this? The integral of sine will be something like negative cosine, and you've got 9x squared in there. If you differentiate that, 18x will come to the front, and it's sort of like 3x. So as long as you can adjust it, you'll be fine. Okay? So sine will go to negative cos. If I differentiate this, I'll get 18x at the front. I don't want that. I want 3x. So I'm going to divide by 18. Okay? Then we give me negative 1 on 6. Okay? So I'll just put in 4 and 0. So that, my friends, is how you do it without drawing a picture, without changing the order of integration, and without describing a region. That's it. Probably took me 10 years to work that out. But gosh, I was excited when I found it. Like, surely this must be known. No, I searched high and low. I couldn't find it anywhere. Maybe people do know it, but you know, they want you to describe the region, and they want you to draw a picture. So how will this help you in the exam? It probably won't. But let's have a look. Let me go in here. So just give me a second. Yep, Mobius. So just give me a sec. Okay. Review quizzes. Let's go into some of the past lab test 2s. Yep. Okay. So if I go here, lab test 2. What? Submit. What did I get? 0. Oh. It's the story of my life. Okay, lab test 2. Yep. Okay. So let's get to one of these. Oh, there's not one. Everyone, get the cameras ready. There. Okay. There's a question. Okay. Now, they're definitely saying change the order of integration, right? They want you to do it a certain way, but they also ask for the inequalities, right? So if you use integration by parts, you can get the answer to part 2, but it doesn't tell you the other stuff that they ask you for, okay? So it's a nice method, but this course is so focused on the method, the original method, that's what they're going to ask you.
What if the numbers weren't so nice for U times V?
Yeah. So yeah, there's like definitely some spots in this solution that you like that might not work out the way you want them to. All the ones that I've looked at. So let me just show this for everyone at home. Okay, so you can see that U times V there, it's beautiful because it just becomes 0, right? Which is great. But let's say it was a constant or something like that, that would also be acceptable. The ones that I've seen, they're always 0. I don't know, there's something magical about them that they just disappear. Okay, now if you can't do it, if you can't do this one, if that's really terrible, it's not going to work. But if you can show me an example where it doesn't work, then I might get the, yeah. And that's a serious question, right? But the way I've seen it, they always disappear. Okay, they always disappear. So people go, shut up. Just tell me what to do. That's fine. Just use the original method. It's the way they want you to do it. They don't want you to use this method because they don't know about it, right? All right, what's happening at home? This is great. I think I blanked out while you were doing the integration by parts. Yeah. How did you do it? Well, if you put in let me put this back. So if you put in x, so this is the thing you're talking about, right? If you put in x equals 4, you're integrating from 12 to 12. That's 0. And if you put in x equals 0, you're multiplying by 0. So it has to be 0. Okay? All right. Now, that is double integrals in a nutshell. Now, that means we're approximately 2 lectures ahead of schedule. 2 lectures. So on Friday, how much revision do you want to do for lab test 1? How much? We can do 1 lesson, 2 lessons, half a lesson. Like, do people care? Right? Should we just sit there for 40 minutes and do the actual test? Right? That could be a bit embarrassing for me, because I said, oh, why aren't you working? How did I do? How did I do? We could do it. We could try it. Right? So let's start. Okay, so let's start with 1 revision, and if people love it, I'll do 2. Is that okay? So you can sort of try before you commit. So, you know, if it's terrible, just don't come. Is that okay? All right. Other questions, comments, anything about the lab test for next week? ID is the most important thing. If you don't have ID, you'll be refused. No calculators. Okay? You should go and test KCalc. You should go and test Desmos. Okay? Before the test. Try it out. Go and find where the rooms are. Oh my goodness. It's like, oh, I couldn't find the room. You've known for like 5 weeks. Go into the room, sit down, log on. Okay? All right, if anyone has any more questions, come on down. If not, I'll see you, some of you on Friday.